Okay, we have here like a really tricky looking integral. We have the integral from 0 to 1 dx over the square root of 1 minus x squared plus 1 minus x squared to the 50th over x to the 99. Okay, there's a lot happening. I kind of like that we have this similarity that we have 1 minus x squared in both, but I'm not really liking x to the 99th there like that. So what I'm going to do first is I'm going to try to get rid of that x to the 99. We're just going to multiply by 1 by multiplying in the numerator and denominator. So doing that, we'll have an x to the 99. In the numerator, we'll have an x to the 99 here. But in this term, the x to the 99s are going to cancel, and we're just going to have 1 minus x squared to the 50th power. And then from here, what I want to notice is, I'm not sure what to do with these x to the 99s right now. That's kind of a lot to handle, but this kind of makes me think of a trig substitution. Typically in this kind of case, we'll substitute using a sine. So what I can do is, I'll make my trig substitution where x equals sine of t. Then dx is going to be cosine t dt, and t is going to be arc sine of x. So I'll make the substitution. So first, I'll take my 1 and plug it in here. Arc sine of 1 is going to be pi over 2, and arc sine of 0 is going to be just 0. Then for x, we're going to have like a sine to the 99th here in the numerator. Then for our dx, we'll have a cosine t dt. Again, we'll have another sine to the 99. Doing the substitution here, this is going to 1 minus x squared is going to be 1 minus sine squared. Well, we can write that as cosine squared, but cosine squared inside the radical is just going to give us a single cosine. And then again, same thing right here. We can write this as cosine squared. Okay, but we're going to have cosine squared to the 50th. But then what I want to do here is just distribute in this. We can, by exponent properties, we can multiply in the 50, and we can write this as cosine to the 100th. And then the thing I notice is I have a cosine in every term, so I can cancel cosine here, and just cancel 1 here, so we're left with 99th power there. And then at this point, you may recognize what we have here. This is actually a classic case for King's principle. You could almost jump right to a solution from here, but we won't do that. We'll go through the steps. But noticing our bounds from 0 to pi over 2, this is going to allow us to make another substitution. I'm going to make my substitution adding pi over 2 and 0. We have pi over 2 minus t. And we can also write this in terms, solving for t, we can write this as t equals pi over 2 minus u. Take our derivative, our dt is going to be minus du. So then we'll substitute here. When we put a pi over 2 and we're going to get 0, and we put a 0 and we're going to have pi over 2. And then for all these t values, we're going to plug in this pi over 2 minus u. Now from here, we have this minus sign here, but what I can do is take this out front of the integral and just use it to swap these bounds and put it back to writing it as 0 to pi over 2. And then from here, the complicated looking thing we have is we have this angle, pi over 2 minus u, but we actually have a formula for that. This is the complementary angle formula, and it's going to reverse all these functions. Here's our complementary angle formula over here to the right. So you can see for like our sine pi over 2 minus u, that's going to change it to a cosine. And then for our cosine pi over 2, it's going to change it to sine. You just have to remember this power, so they're all going to be raised to 99, but then we can get back to just our angle being u. So let me rewrite this and let's see what we have. Okay, nice. So now we're just back to u for our angle. Now for my next step, what I want to do is we want to do a variable change. What I'm trying to set up here is I want to go back to an earlier version and add them together. So we need to be all in the same variable. I'm going to go back to t. We could go back to anything. I'm going to go back to change my variable to t. It's a definite integral, so changing variables is not a problem at all. We can change to whatever we want. So I'm going to change to t, and don't forget the du. And then from here, what I'm going to do is we're just going to call our original integral's I. We manipulated it to this integral, which we'll call I, and this is still I. So what I'm going to do is take this copy I with sine in the numerator and this copy of I and add these two together, and let's see what we have. Now we are allowed to add these together because again, we have the same variables, same bounds, and we have the same denominator. So I was able to put together our numerators like this. And the beauty of that is we've got the same numerator and denominator. So this whole integral is actually just 1. So we'll integrate this. Integrating 1 is just going to be t, and we just need to evaluate that from pi over 2 to 0. That, of course, is going to be pi over 2 minus 0. One final step to finish this off. This is actually 2 copies of the integral, so I need to divide by 2 here and divide by 2 here, and that's going to give us the final solution of pi over 4. Sometimes I think pi over 4 is a pretty good guess on these problems. So anyway, if you see something that looks like King's Principle, maybe just guess pi over 4 and it could work for you. Anyway, I thought it was a pretty good problem. We'll stop it there. Thanks everyone for watching today. Have a great day.